In section 10.4, you learned about exponential functions. Exponentials are pretty straightforward and familiar. In section 10.5, you'll be studying logarithmic functions. Although logarithms can get confusing, keep in mind that a logarithm is simply the inverse of an exponential function. So in the same way that subtraction and addition have a relationship, and multiplication and division have a relationship, exponential functions and logarithmic functions have that same relationship. They are inverses of each other. Take some time to go through the first 2 pages of the notes of section 10.5, and when you get ready to work the logarithmic and exponential equations, starting with example number 5, I'll go through those with you. If you've already completed that, let's begin in solving these logarithmic equations. In example 5, we'll be solving logarithmic equations, and example 6, we'll be solving exponential equations. So again, a logarithm is the inverse of an exponential function. So it undoes an exponential function, just like subtraction undoes addition. So very quickly, if you were to solve a very simple equation like this, x plus 1 equals 5, how do you solve that equation? Well, you have to isolate x, and we know we're supposed to isolate x by subtracting 1 from both sides. It's very intuitive. But how do you know to subtract 1 from both sides? You subtract 1 from both sides because it's the opposite of addition. It undoes that operation. And of course, we get a very simple solution to this equation. That same principle of inverse functions is what we're going to apply to solve a logarithmic function. So example 5a, we have log base x of 8 over 27 equals 3. We want to undo the operation represented by that logarithm. That is, we're going to convert from logarithmic form to exponential form. So we're going to take the base of the logarithm, that's the subscript x. We're going to raise it to the exponent indicated on the other side of the equal sign, that's 3, and we'll set it equal to the argument of the logarithm. The argument of the logarithm is simply what's to the right of the logarithm. The x is the base, the 8 over 27 is the argument. So we have base x, exponent 3 equals 8 over 27. Now observe that pattern. It's the same way every time. Base x to the exponent of 3 equals 8 over 27. Then you no longer have a logarithmic equation, you have a polynomial equation. We have x cubed equals 8 over 27. To solve this equation for x, we need to undo the operation indicated by that exponent. To undo a cube, we use the inverse or the cube root, right? It's the same principle. So on the left side, the cube root of x cubed is x. And on the right side, I'm going to evaluate the cube root of both the numerator and the denominator. The cube root of 8 is 2, and the cube root of 27 is 3. So the solution to our equation is x equals 2/3. Let's move on to the next one. The pattern is the same. I'm going to take it out of logarithmic form and put it in exponential form. So we'll start with the base 4, raise it to the exponent 5/2, and set it equal to the argument. This looks like 4 raised to the 5/2 equals x. And what do you know? We just isolated x, even if it was by accident. X equals 4 to the 5/2. We do have to evaluate 4 to the 5/2. If you'll remember, if you have some number raised to a rational or a fractional exponent, that base becomes the radicand. The denominator of your rational exponent becomes the index of the radical, and the numerator becomes the outside exponent. So if I can apply that pattern to 4 to the 5/2, the base 4 becomes the radicand. The index of the radical is the denominator 2, although you don't have to write that one. And the numerator becomes the outside exponent. So to evaluate this, we'll start on the inside. Notice we have the square root of 4 there. So the square root of 4 is 2, and then we raise that to the 5th power. 2 to the 5th power is 32. So the solution to our equation is x equals 32. Now both of those equations had the same basic pattern. We were just converting into exponential form. But when we get to example C, notice we have two logarithms. So before we can convert to exponential form, we have to use our new log properties to condense the logarithms into a single logarithm and then convert to exponential form. So let's begin. We have log base 2 of x minus log base 2 of x minus 1 equals 1. On the left side, we're subtracting two logarithms. One of our properties says that if we're subtracting two logarithms, we can condense them into a single logarithm with the same base, and in the argument position, we're going to divide those arguments. So I'm going to take the first one, x, and divide it by x minus 1. Okay, so when we're subtracting logarithms and we want to condense, we condense them into a single logarithm, and the new argument is the quotient of the two original arguments. Now that we have a single logarithm, we can convert to exponential form. So we're going to take base 2 to the exponent 1 equals x, and we no longer have the problem of the logarithm. So we have base 2, exponent 1 equals argument. Now at this point, you have to stop and reassess the equation and determine what type of equation it is and what you should do. In this case, it looks like we have a rational equation. So I'm going to solve this by multiplying both sides by x minus 1. I want to get rid of that denominator. So I'm going to multiply the left and the right by this factor x minus 1. When I do that, the x minus 1 cancels on the right side, and I can distribute the 2 into this binomial on the left. So this brings us to 2x minus 2, and on the right side, all that's left over is x. This is a simple linear equation. We can solve this by subtracting x from both sides to combine our x's, and we can move that constant to the other side by adding 2 to both sides. So we end up with x equals 2. So the solution to our equation is x equals 2. On example D, again, we have two individual logarithmic terms. We need to condense to a single logarithm before we convert to exponential form. This one's different than the previous one because instead of subtracting the logarithms, I'm adding the logarithms. When we subtract the logarithms, it indicates a quotient or a division that occurs in the new argument. When we add two logarithms together and condense into a single logarithm, we're going to multiply the two original arguments. Okay, so remember, subtraction and division go together, addition and multiplication go together. Notice the base is omitted on this logarithm. If there's no base that's written, it's understood to be the common base or a base 10 logarithm. So although it's not written, we know that there is a base 10 there. Now that we've condensed the logarithm, we're going to convert to exponential form, base, exponent, and argument. So our new equation becomes 10 to the first power equals x times x minus 3. So we've kind of wiggled our way out of the logarithm. And again, we have to stop and reassess the equation and determine what type of equation it is so we'll know how to solve it. Notice on the right side, if I distribute that x, it becomes a quadratic equation. We solve quadratic equations by factoring or by quadratic formula. But in either of those two cases, it has to be equal to 0. So let's go ahead and subtract 10 from both sides, and we have our quadratic now equal to 0. We can solve this one by factoring. This one factors as x minus 5 times x plus 2. When we set each of those factors equal to 0, we get two apparent solutions. One solution appears to be 5, the other one appears to be negative 2. However, only 5 is the solution. X equals negative 2 is what we call an extraneous solution. That means it's extra. It comes out of the algebra, but it doesn't actually solve the original equation. Why does it not solve the original equation? Well, notice x is equal to something negative. If I go back and look at the original equation, and I'm just going to pick on one term, although this applies to both, but if I try to plug a negative 2 in for x, it's an undefined operation. So the logarithm of anything negative, so the logarithm of a negative number is undefined. It's actually an imaginary number, okay? If you think about the graph of a basic logarithm, it looks something like this. And there's a boundary line on the y-axis. The domain of a logarithmic function is 0 to infinity. That's basically telling me the argument of the logarithm must be positive. What I'm plugging into the logarithm must always be positive. So if I try to plug in something that's negative, it's not going to balance the original equation. So the only solution to this equation is x equals 5. Notice the commonality between all of those equations. We condense the logarithms into a single logarithm and then convert to exponential form. If you get that pattern, those logarithmic equations are not too difficult to solve. Now, let's switch modes. Let's talk about solving exponential equations. Just like we used an exponential equation or an exponential operation to undo a logarithm, we're going to use a logarithm to undo an exponential operation. Again, we use subtraction to undo addition. We use division to undo multiplication. I'm always solving equations applying the principle of inverses. So if I want to solve this exponential equation, 3 to the x equals 5, I've got several options here, but in order to stay consistent with the book, we're going to go with the practice of taking the natural log of both sides. So anytime you want to solve an exponential equation, take the natural log of both sides. Notice we're applying a function to both sides. Now, by the way, on MyMathLab, make sure that you type this in as LN, not IN. Some online students make that mistake. The abbreviation for natural log is LN log natural. So type it in with a lowercase l, not an uppercase I. Just a heads up on your MyMathLab there, it'll cause a syntax error. Now, when I apply the natural log to both sides, that allows me to apply that log property that says I can move that exponent down in front as a coefficient. So on my next step, I have x times natural log of 3 equals natural log of 5. Then we can divide both sides by this constant, natural log of 3, to get our solution. Keep losing my notes here. There we go. X equals natural log of 5 divided by natural log of 3. Now, if you were wondering why does this feel different than it does with logarithms, it's because we're using the natural log. A natural log is an ordinary logarithm with that natural base called e. The reason that we use natural log is because it's convenient to evaluate this on our calculator. So natural log can be located on your calculator on the left side of your keypad where you see the ln. So for example, let's suppose I wanted to check my work by taking my solution and plugging it into the original equation for x. I would have to evaluate 3 raised to the exponent, natural log of 5, close parentheses there, divided by natural log of 3, and press enter. I notice the result is 5, and that's what I had on the right side of my original equation. So it makes it very convenient to solve or to check with our calculator. It also makes it convenient to approximate. So if I want an approximate value of that irrational number, I would just type it into my calculator and round the result. This is approximately 1.465. So we could say the approximate answer is 1.465. This is what we call the exact answer. This is what we call the approximate answer. The exact answer makes it balance perfectly. The approximate at least makes sense to our brain. What's the approximate size of that number? By the way, this is equivalent to the solution log base 3 of 5. Maybe that's what you were thinking. Because if I take 3 to the x equals 5, the original exponential equation, and I convert it into logarithmic form, it's going to look something like this. That is a perfectly acceptable answer if you want to use that method. However, in order to get that log base 3 of 5 into the calculator directly from the keypad, I'd have to apply this change of base formula with natural logarithms anyway. So for the most part, your book, MyMathLab, will express all the solutions in terms of natural logs. Okay, so that's the route I'm going to take as well. Let's practice the next example. The same procedure. We want to begin by taking the natural log of both sides. Now watch your levels when you write this. Make sure you understand what's a superscript, what's a subscript. Again, once you apply that logarithmic function, the natural log, which is just log base e, then that allows you to move your exponent down in front as a coefficient. So on the next step, we have 2x natural log of 3. And on this one, since I'm moving a binomial exponent, I have to put that exponent in parentheses. Did you notice we're no longer in the situation of having an exponential equation? We have a new type of equation. But the presence of our logarithm allowed us to unlock that exponential operation. Now, in solving this next equation, make sure you understand that this ln of 4 is one cohesive number. I can't ever separate a natural log from its argument. So I'm going to treat that as one constant, and I'm going to distribute it to both terms inside parentheses over there on the right side. So I have 2x natural log of 3 equals x times natural log of 4 plus natural log of 4. Now, I want to collect all my x's together on one side. We'll go to the left, and everything without an x we're going to leave over there on the right. So what I need to do is subtract x, natural log of 4, from both sides, so that everything containing an x will land over there on the left side. So we have 2x, natural log of 3, minus x times natural log of 4 equals, and we're left with a natural log of 4 over there on the right side. Notice on the left that each of my terms has an x, so I'm going to factor it out as a greatest common factor. That leaves behind 2 natural log of 3 minus natural log of 4. So to finish this equation, I'm going to notice x is being multiplied by some number. So to undo that multiplication, I use division, which is the inverse of multiplication, and I'm able to isolate x. So dividing both sides by this number, it's just a constant, looks like a big complicated number. We end up with x equals natural log of 4 divided by 2 natural log of 3 minus natural log of 4. May not be pretty, but it is exact. If we want to approximate it, we can use our calculator to evaluate it. Now, we have to be careful when we plug this into the calculator because I do have an operation going on in that denominator. So I'm going to intentionally add some extra parentheses around that denominator. So we have on the top natural log of 4, and we're going to divide by open parentheses for your denominator, and our denominator was 2 ln of 3 minus ln of 4. Make sure you close parentheses behind each argument of the natural log. Now I'm going to close parentheses for my denominator. If it turns out that your particular calculator has a two-dimensional format, that is, when you type in natural log of 4 divided by and it looks like a fraction, then you won't need those extra parentheses in the denominator. But if yours looks just like mine, make sure you get parentheses around that denominator. So if we round this to the nearest thousandth, the 5 causes the 9 to round up, we'd end up with 1.710 for our approximation. So the squiggly equals there represents approximately equal to. We've got one more exponential equation to solve. This one, notice, involves the natural base e. So when we use the natural log, you're going to see some simplification occur. The first thing that I want to do is isolate that exponential term. So I'm just going to sneak right in here and divide both sides by 5 so that my exponential part is by itself. We have e to the 0.1x. You can either write it 9 over 5, or you can evaluate it to get 1.8. At this point, I'm going to apply the natural log to both sides, just like we've been doing, which again allows me to unlock this exponential operation by moving that exponent down in front as a coefficient. So we end up with 0.01x, natural log of e, equals natural log of 1.8. Now, anytime you see the natural log of e, this represents what exponent could I raise e to in order to get e? Remember, a natural log represents an exponent. Well, the only possibility there is 1. If you forget that, you can always double check it on your calculator. Natural log of, now the e by itself is over there on the right side of your keypad above your divide button. So to access it, I do my second key and then my divide button and evaluate. So natural log of e is always 1. So when that pops up in an equation, it makes it really convenient. So this simplifies to 0.01x equals natural log of 1.8. Let's divide both sides by the coefficient of x to isolate our variable, and we have our solution. X equals natural log of 1.8 divided by 0.01. We can also approximate this with the calculator. Natural log of 1.8 divided by 0.01, and we end up with, if we go to the nearest thousandth, 58.779. So our approximate value, 58.779. Do I remember that correctly? 58, yes. Okay, so that is our exact versus approximate. Now, once you feel confident about your exponential and logarithmic basic functions, you're ready to return to Chapter 12, where we begin differentiating exponential and logarithmic functions. See you soon. Thanks for listening.